Let's continue with lesson 14, looking at disproving conjectures with counterexamples. This is going to be a very short lesson. Really all it is the definition of a counterexample. A counterexample is an example that proves a conjecture or statement false. So you're proving something wrong. So there's a conjecture, and if you prove it wrong, that would be known as the counterexample. So in example 1, it says, if a triangle is isosceles, hopefully you remember that an isosceles triangle has two congruent sides, then it is acute. Well, part A wants us to identify the hypothesis and conclusion. Just a refresher, hypothesis is labeled with a P, and it is the part that is after the if statement and before then. Then it wants us to label the conclusion. That is always after the then statement and labeled with a Q. So it wanted us to do that first, just a refresher on hypothesis and conclusion. Then it wants us to find a counterexample to the conjecture. It's saying if you have an acute triangle, that's isosceles. Well, sure, that is an example, but is there another example of a triangle that is isosceles but is not an acute triangle? First, you would need to know all three triangles classified by angles. You have acute, you have obtuse, and you have right triangle. So can obtuse or right triangle be isosceles? Well, yes it can. If you have a right triangle, if I drew this, the legs are the same length, and it's a right triangle. So that would be a counter. I'll just put C, counter example. And that's an obtuse you could do as well. All right, if those were congruent, that would be a counterexample as well. So that's all there is to lesson 14. I'm not going to go into any more detail. Counterexample is simply proving the statement wrong. So let's move on to lesson 15, talking about polygons. We looked at the triangle specifically and in detail recently, but now we're going to look at polygon. The definition of polygon is a closed plane figure by 3 or more segments. You cannot have a polygon unless you have at least 3 lines. Examples of polygons. Here you have a polygon that has 1, 2, 3, 4, 5, 6 sides, so that would be a hexagon. There's a polygon with 4 sides, so you could call that a quadrilateral. And this is a polygon with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 sides. 12-sided polygon would be referred to as a dodecagon if you look at it in more detail. But those are examples of polygons. They are closed plane figures with at least 3 line segments. Just to show you what some examples of not polygons would be. You have a circle, it's not a polygon. It's not 3 or more segments, it has to be segments. You have a semicircle, you have 1 segment, but then that is a curved line. This one is not closed in, and this is a 3-dimensional figure. Sure, this rectangle is a polygon, but the whole shape in and of itself is not a polygon. It is 1 plane figure, and that cube when you go 3-dimensional, you have multiple planes. Only 2-dimensional figures have 1 plane. So those are some examples of polygons. On page 90, you have a whole chart that shows the details of different polygons and their names for how many sides they have. So you can look at that on your own. I'm not going to look at that right now. But I do want to look at these polygons here and classify them by whether they are equiangular or equilateral. A regular polygon is both equiangular and equilateral. All the sides are the same length, all the angles are the same measurement. So if we look at polygon A, it has equilateral sides. Okay, so it's equilateral. I'm just going to abbreviate that. It's equiangular. So therefore, it is a regular polygon. For B, all we have is equiangular. If it's only equiangular, it is not considered a regular polygon. You would actually call that an irregular polygon. C is only equilateral, therefore it's also irregular. And then D is not equiangular or equilateral, so naturally that would also be irregular. But that's the difference between regular and irregular polygons. Then you have a couple more ways to classify polygons as well. You can classify them as convex or concave. Now, in order to know whether it's convex or concave, you generally look at the diagonal of a polygon. And a diagonal is simply a segment that connects two non-consecutive vertices. Vertices is where two of the lines meet. So one line, another, and then it would have to connect with another non-consecutive, that would be consecutive or adjacent, another non-consecutive vertice. Convex, any line that you draw from any vertex that is non-consecutive, if all the lines that are diagonal would be inside the polygon, then it would be referred to as convex. Over here, concave, if you have two vertices that are non-consecutive, where you could draw a line between the 2 points and it's exterior to the polygon, that would be known as a concave polygon. And concave, it is how it sounds. It looks like it makes a little cave. But that would be a concave polygon, and you find those with the diagonals. The last part about polygons that we're going to talk about when identifying them is by angles. We're just going to talk about interior and exterior angles, and it is exactly how it sounds. Interior angles, inside, and then exterior, outside. You have to make sure that you label angles properly. So if we're talking about this angle right here, it's not just angle C, because if you said angle C, it could actually still be the outside the polygon. So what you would have to say is some interior angles are angle BCA. That's an interior angle. Angle ABC. That's an interior angle. An exterior angle, well, we have the little line right here. An exterior angle example would be ADE. Angle ADE would be an example of an exterior angle. And that's the last thing we're going to talk about with polygons. And so that's just kind of learning how to classify them by sides, whether regular or irregular, and angles. So that concludes lesson 15.